All right. I'm really excited to be here with all of you at Google Cloud Next. My name is Sebastian Mugazambi, and I'm a product manager for AI infrastructure at Google Cloud. I'll later be joined by Dean Ledersdorf, who is CEO and co-founder of Descartes AI. For the first half of this session, I will deep dive into the latest advancements that we've made to the TPU roadmap. While I will set the stage with some of the major use cases and motivations for designing TPUs, I plan on providing a technical deep dive into the key technological improvements we have made to the 8th generation TPUs. From the silicon to the differentiated scale and the low latency system improvements that we've made. Later, I will invite Dean to share details of the frontier AI model work that Descartes is doing in developing world models, including how TPUs are architectured for this new frontier of AI models. Before we deep dive into it is crucial to understand the challenges faced by every stage of the entire AI model lifecycle. Starting with training. In only 1 year, AI model sizes have grown by over 10x, reaching 10 trillion parameters, with increased complexity across multiple scaling dimensions. Additionally, time to market for newer and more capable AI models is of paramount importance, which means training these extremely large and complex models requires reliable AI infrastructure that delivers very high goodput. Even in the post-training phase of frontier model development, we're seeing a rise in reinforcement learning as a way to guarantee agentic reliability. And when the model is fully trained and launched, and you still have to make some crucial and critical decisions in your serving infrastructure. For example, in LLM inference, efficiency is a tug-of-war between two fundamentally different compute profiles. Prefill is compute intensive, requiring faster time to first token, while decode is memory bandwidth bound, requiring lower inter-token latency. Optimizing for one often compromises the other. At Google, we have spent the past decade solving the problems by building industry-leading, reliable, performant AI infrastructure that scales, cost, and power efficiently to meet the evolving demands of frontier models. When we developed TPUs at Google, we designed them to reliably deliver the best in-class performance per dollar and performance per watt for all key AI workloads, while maintaining high absolute performance at very large scales. TPUs work in conjunction with our AI hypercomputer stack to deliver value for our customers' AI workloads, including fast building and deploying with GKE. It also includes flexible consumption models, open software support for frameworks like JAX, Keras, and PyTorch, and performance-optimized hardware that includes TPUs, GPUs, storage, and networking. Some of the most exciting innovations that you have seen throughout this week is powered by TPUs. Our generative AI models coming out of DeepMind are trained and served on TPUs. AlphaFold was trained on TPUs to solve hard problems, like predicting protein structures resulting in a Nobel Prize in chemistry. All of this entirely enabled on TPUs. In addition to innovations coming out of DeepMind, TPUs power many of Google AI-driven services, including search, translation, image recognition, and more. By making them available in the Google Cloud Platform, we're able to pass on the same value proposition to our external Google Cloud customers. Since 2015, we've made improvements to make TPUs faster, more scalable, and very efficient, including introducing ICI and 3D torus topology, liquid cooling, vertical power delivery, integration with the AI hypercomputer stack, and native lower precision numerics. Speaking of improvements, on Wednesday, we announced our 8th generation TPUs. Let's take a close look at some of the giant leaps in advancements that we have made to these TPUs.
Over the last few years, we have all seen the evolution of AI. Model sizes are growing exponentially. The new frontier models will reach trillions of parameters. Models have evolved to keep up with the changing demands. The infrastructure needs to evolve as well. I'm thrilled to announce that Google will be launching 2 8th-generation TPUs. TPU 8T and TPU 8i.
All right. Behold, the future of AI compute in the palm of my hand today. These aren't just chips. These TPUs are specialized systems designed specifically for the unique needs and demands of the agentic era. And looking ahead, they will power the emergence of frontier models like world models. This is all really exciting, and we can't wait to put the power of TPU 8T and 8i in the hands of our customers later this year. Now, we've made some major upgrades and improvements in the 8th generation TPUs. From the specialized silicon and high bandwidth interchip interconnect topologies to scale-out networking capabilities. Now, let's start by taking a close look at TPU 8T. TPU 8T is our training workhorse that is optimized for pre-training the world's largest AI workloads. A single tensor core on TPU 8T introduces FP4 lower precision support, delivering 4x the compute compared to 7th generation TPUs. We are still leveraging systolic arrays to minimize memory access, which is a common bottleneck in traditional processors. They keep data moving and being processed in a pipeline fashion, which dramatically increases the speed of matrix operations. We have also doubled the interchip interconnect ICI bandwidth. And we continue to leverage Google TPU's proprietary sparse core technology, not only for further accelerating embedding heavy workloads, but also enabling LLM workload speed up by adding the new integrated LLM decoder engine. For an AI chip, quantization is key to efficiency. In prior architectures, sub-channel scaled multiplications relied on the VPU and for block scale multiplication. This created VPU overhead. With TPU 8T, we have natively moved the block scale multiplication inside of the MXUs. What does this mean for you as a user? You gain 0 VPU overhead for quantization. Additionally, we support very small block sizes, so as low as 16 for FP8 and 32 for FP4. This results in better signal-to-noise ratio for quantized data. Ultimately, this MXU integration delivers higher model quality and very high low-precision flops utilization, ensuring your workload is not bottlenecked and trains faster with higher throughput. To further speed up your workloads, TPU chips have a sparse core. This is a specialized core processor integrated into the TPUs themselves. This is only unique to TPUs. By overlapping the compute-heavy dense computations in the tensor core with the sparse embeddings computations offloaded to the sparse core, TPUs further accelerate embeddings-heavy workloads. Now, I'm pleased to announce that in TPU-AT, we have introduced an LLM decoder engine to the sparse core. In TPU-AT, you can utilize the same overlapping technique to overlap compute-intensive prefill in the tensor core with the memory bandwidth-bound decode offloaded to the sparse core LDE. Although TPU-AT is optimized for training, this addition is a huge bonus for TPU users who want training and serving fungibility on TPU-AT. As you go beyond a single TPU-AT chip and train across multiple chips, transferring data between one chip's HBM to another chip can be a bottleneck. That's why we're introducing TPU Direct in TPU-AT. TPU Direct bypasses the host CPU and DRAM by enabling direct data transfer between TPU HBM and network interface cards, or NICs, reducing data transfer time for distributed training. Eliminating hops through host memory, TPU-AT fully utilizes available NIC bandwidth for higher throughput. This further accelerates collective operations across data center networking, offering the high bandwidth and low data transfer latency necessary for massive scale MOE scale training. TPU Direct now has two use cases. Firstly, TPU Direct RDMA. This capability allows a TPU to skip the host DRAM when moving data directly in and out of the HBM of another chip. This drastically improves data transfer speeds for thousands of TPUs that are working together to train some of the world's largest AI workloads. Secondly, TPU Direct Storage. This allows pulling hundreds of petabytes of data directly into the Silicon's HBM from the managed storage like Lustre TNT, which drastically reduces data ingestion latency and increases bandwidth. TPU Direct Storage helps keep the data moving and keeps the TPU cores consistently busy, leading to faster model training time. When it comes to scaling up, TPU-AT chips have 6 copper interchip interconnect ICI links. They are connected in a nearest neighbor fashion into a cube of 64 chips that is equivalent to a single rack deployed. Cubes are connected to each other over optical circuit switching, which offers high flexibility to form a 9,600 chip 3D torus topology superpod, which is the ICI domain. TPU-AT ICI domain delivers 121 exaflops of FP4 compute with 2 petabytes of shared HBM at an extremely fast 19.2 terabits per second ICI bandwidth. Beyond a single ICI domain, TPU-AT chips can scale out utilizing our newly introduced Virgo networking fabric, now complementing Jupyter, which is responsible for WAN, host, and storage traffic. Now, Virgo is a collapsed 2-layer, fully non-blocking fabric built for high scalability and bandwidth. It offers high resilience and across multiple independent planes, and this single fabric, it is at the scale of the entire data center building, connecting over 134,000 TPU-AT chips at a 4x the bandwidth prior to previous TPU generations, with 40% lower latency. The scale-out story does not end with a single Virgo fabric. Over 8 of these fabrics can be connected, enabling training across a staggering 1 million TPU-AT chips. This is over 100 TPU-AT superpods, each delivering 121 exaflops of FP4 compute. Now, with all of these technological advancements, TPU-AT offers over 2.7x better performance per dollar and 2x better performance per watt for the largest AI workloads compared to prior TPU-7X. After TPU-AT has delivered this immense value for training, the story does not end there. So looking ahead at the agentic era, high latency inference could force agents to think slower than the environment that they're tasked to work within and operate within. This leads to systematic failures. Agentic use cases often require multiple internal reasoning and sampling loops to increase accuracy at which they perform their tasks. Without a hyper-optimized inference solution, the compute text for these agents becomes economically unsustainable. That is why we're introducing TPU-8i, a second 8th generation TPU system. This is purpose-built for ultra-low latency serving and sampling workloads. The TPU-8i ASIC features a very large SRAM. This enables storing frequently accessed data like KV cache closer to the MXU where the majority of the computation is happening, reducing the tax for constant fetching from memory. TPU-8i chips are all interconnected by 2x the ICI bandwidth of prior TPU generation 7X. The two tensor cores are supplemented by our newly integrated collectives acceleration engine on TPU-8i. At Google, we take a fully ASIC integrated approach to architecting for the demands of ultra-low latency inference. So instead of using an Ethernet cable to connect, another rack-level component for lower latency inference, we have built the TPU-8i ASIC die that is fully integrated with a collectives acceleration engine and a very high on-chip SRAM. This combination of a very large on-chip SRAM, which keeps frequently accessed data like KV cache close to the compute units to drastically reduce memory access latency, and the specialized collective acceleration engine, which offloads and speeds up inter-chip communication primitives, enables TPU-8i chips to achieve ultra-low latency inference. Beyond the single chip, TPUs pioneered the 3D torus topology for interconnecting TPUs for large-scale training. However, to further reduce chip-to-chip latency by over 50%, we are excited to introduce a new hierarchical, fully connected board flight topology to TPU-8i. Imagine this: 4 TPU-8i chips are fully connected on a board. 8 of these boards are fully connected into a group of boards, and 36 of these groups are connected via flexible optical circuit switching into a pod of 1,152 TPU-8i chips. If you compare this to the 3D torus, board flight topology reduces the maximum network diameter between any two chips in the pod from 16 to 7 hops, drastically lowering latency for all-to-all communication patterns that are critical for low latency inference of MOEs. The max 7 hops in the TPU-8i board flight topology ensures a 58% lower network diameter. This reduces latency by 2x compared to 3D torus. Now, as I mentioned, we complemented this with the massive on-chip SRAM for larger KV cache hosting and a collective acceleration engine to deliver 80% more performance per dollar for low latency serving compared to Ionode TPU-7X. TPU-8i is truly built for instant reasoning that makes the millions of agents executing tasks to really execute at unprecedented speeds. Now, with TPU-AT offering reliable, scalable, and cost-efficient training, and TPU-8i delivering ultra-low latency latency and cost-efficient reinforcement learning, the 8th generation of TPUs truly deliver value for every stage of the agentic development cycle. We're also heavily investing in our software ecosystem. To fully leverage the power of the 8th generation TPUs, I'm pleased to announce that we will be starting with PyTorch. We are committed to delivering a native PyTorch experience on TPUs. With the native PyTorch experience, our North Star is very simple. No new APIs, this is just the PyTorch you know and love. Bring your existing PyTorch code with minimal changes to work with TPUs and leverage familiar features like eager mode. Secondly, this support lets you unlock the efficiency and price performance of TPUs with PyTorch. The solution is optimized for all parts of the AI lifecycle, from training to post-training, from pre-training to post-training, and also serving. It is designed to linearly scale your models to hundreds of billions of parameters. And finally, we're deeply embedded as part of the PyTorch community. TPUs are now a first-class PyTorch backend, and we offer broad ecosystem support for major PyTorch projects. So what does this look like in practice? These code differences represent our vision. On the left, you have a standard PyTorch training script in the CUDA environment. On the right is what you had to do today with PyTorch XLA. You can see the amount of red-lined changes you need to make. Now, however, this is the future of PyTorch on TPUs. The code on the left is the same CUDA-based script, but on the right is our native TPU backend. You only need to change 3 lines of code related to device initialization. The core training loop is identical. This makes it easy for TPU users to maintain their familiarity with the PyTorch ecosystem as they adopt TPUs. Now at Google, we're always looking ahead to predict what is the next frontier of AI models that will push the boundaries of our AI infrastructure. We believe the next frontier is world models. These are generative models that understand and simulate the workings of the real world, giving agents a risk-free environment to act and learn before deploying in the real world. Applications of world models also include physical AI for robotics training. TPUs are used across multiple industry verticals. Global AI labs are really pushing the boundaries of these frontier foundational models, like world models on TPUs. Descartes AI is one of those AI labs. And speaking of which, I am honored to introduce Dean Ledersdorf, the CEO and co-founder of Descartes. Dean completed his PhD at the Technion Israeli Institute of Technology. Think of it as the Israeli MIT at the age of 23, becoming then the youngest PhD graduate in the institute's history. He finished his studies in just 4.5 years while simultaneously leading research at Unit 8200. Please join me in welcoming Dean.
Thank you, Saba. Thank you, Saba. Hi, everyone. Very, very exciting to be here and announce what we've been working on together. So, at Descartes, we're a foundational model company, and we're working at the frontier of world models. World models, they're a new category of AI, and we believe that they will enable agents and AI to move from the virtual world into the physical world. Today, with world models, we're already changing how we behave online. They're creating new virtual experiences for consumers and users all around the world through AI video. Today, as these models are already creating these experiences online, we're starting to see how they're starting to shape physical AI and let robotics play out what will happen in the physical world by creating an entire simulation of it. The tech that we build at Descartes, it enables orders of magnitude efficiency improvements for current use cases of low latency inference, such as agents and LLMs, and also opens this completely new frontier of very low latency world models for online new experiences and for physical AI. So at Descartes, we really take a complete full stack approach. We go all the way from writing assembly for accelerators, assembly for TPUs, all the way up to doing model pre-training and post-training ourselves. Now, we're obsessed with efficiency. We're obsessed with squeezing every last drop of performance. That's why our logo is a lemon. And to do that, we really have to design everything from scratch. We design the foundational models themselves, and we go all the way and we build an optimization infrastructure that actually looks at the chip, looks at the hardware circuits, and optimizes inference for low latency. With what we've built, we're already deployed in production to speed up agents today at the most cutting-edge speeds and to enable these new world models to emerge. Therefore, because we're always constantly looking out to what new accelerators are in the market, what can deliver new cutting-edge performance for low latency, we're very excited when 8i was announced, and so we took a look at it to see what it can do for low latency workloads. To train world models, we show them everything. We show them everything about the world. We show them text, we show them images, we show them video, and through this, world models gain two items. On the one hand, they gain intelligence. They know how to think like an LLM, like an agent. But on the other hand, because they're seeing millions of hours of video, they also understand structure. They understand the world, they understand physics and dynamics. And by combining this, world models are really able to combine both intelligence and physical structure. This is why we believe that world models are a critical step on the path to AGI, and they will enable over time AI to move from the virtual world into our physical world by creating these new, completely new cutting-edge use cases. So at Descartes, we have two models. We have Lucy and we have Oasis. Lucy, it takes the world, takes any live video stream and injects AI into it. We're seeing it create completely new experiences in social media, in gaming, ads, e-commerce, and even on cameras inside robots. Now, we're going to see a demo of Lucy in just a second of really what the power of Lucy is. Oasis, on the other hand, is a complete world model that takes physical structure and uses it to create an entire world from scratch. Oasis is creating now a new platform for gaming, and it's also at the same time enabling robotics and physical AI to imagine and create structure in a virtual reality that simulates the real world. We pioneered world models a year and a half ago when we launched the first ever world model that was ever released to the public. Last month, we launched Lucy 2.1, our 6th generation world model. And with Lucy 2.1's launch, we saw it completely transform industries. We began with e-commerce and virtual try-on, and continued all the way into streaming and social experiences, among other verticals. And right now, let me show you a demo of really what we can do with Lucy. So everything that you see right now on this stage is happening live. You can see me right now here in this suit, but I dressed up not formally enough for this conference, so Saba made me put this on. Now, had we wanted a completely different Vegas experience, I could have been in a race car suit. Everything you see right now is being generated right here on the stage. And this is what it'll probably look like at Next 27 when robots completely change what we can do. Now, thank you. Now, I don't just have to change myself, because Lucy is understanding the world completely from scratch end to end. It can edit everything. So we can hop into a movie, or we can completely change styles and go into an anime situation. Whoops, sorry. Or we can completely imagine what happens after robots completely take over, and this is what we look like. So now if we go back to the slides, everything you just saw right now was being generated real time here on this stage. This is the only model in the world that has these capabilities to run live and take any video stream and inject AI into it with no latency at all. So the first industry we're seeing this change is e-commerce. This is literally how you use your model. You can take any image and just drag it onto your live video. It can be a couch, it can be clothing, you can even interact with it. You can move around in it, it understands how to take an image and inject physics and inject how these objects interact with each other. This is the power of what we get when we train a world model, both on text and intelligence, and on understanding physical structure. It knows how to interpret, for example, just an image, and add to it all the layers of physics, all the layers of dynamics. You can see how the fabric moves. You can see how a person turns around and completes the object for them. All this is end-to-end. There is no specialized system surrounding it. It's pixels in, pixels out. With live streaming, we've seen it completely change how streamers interact with their audiences, creating completely new immersive experiences that were just impossible before. In gaming, we're creating a new foundation layer. All games can now be run on top of these real-time models to create infinite generated worlds that generate on the fly, per user, dynamically on what's happening live. You can just take a story, a concept, and turn it into this entire virtual world that you can play in. Now, all this tech is great, and it's creating completely new experiences in hundreds of billions of dollars in markets that will be revolutionized over the coming years. But the holy grail of world models is physical AI. These models are able to let AI understand structure, understand physics, understand how the world works. And so what we're already starting to see happen is that robots train themselves inside these world models. They use the world models to be a risk-free simulation of the real world so that before they act in the real environments, they can understand and they can predict what will happen when they perform certain actions in this virtual world model and then take it and apply it to the real world. So we're very, very much excited by the new frontier that these new models are unlocking. So far we had text agents, we had LLMs, and they were just able to go ahead and supplement all knowledge work on the planet. This is reshaping the internet and leading us in a few years to completely changing physical AI and robotics. But to enable all this, it's not just training the model. We have to go really deep down. We literally write assembly for TPUs and for AI accelerators in general. We have to understand the hardware circuits to enable this workload. Now, you might ask why. The reason is that the workload you just saw on the screen is probably one of the most complicated workloads at the cutting edge of AI. Every frame we saw right now was roughly 8,000 tokens. So we're generating 8,000 tokens per frame at tens of frames per second. Sometimes, in some use cases, we even go to 100 frames per second. So that means we're generating hundreds of thousands of tokens every single second with an incredible latency constraint that we have to get a frame out every few milliseconds. This is probably the most intensive AI workload from a computational standpoint and challenging from a hardware and silicon standpoint. And it really has no other parallel in AI. So to really enable this at Descartes, we had to build what we call the Descartes optimization stack, DOS, and it built the best infrastructure for serving low latency models. This infrastructure enables very fast agents today, as well as world models and physical AI, all running at the highest possible efficiency in the industry. So together with Google's announcements of yesterday of TPU 8i, we believe that 2026 is being shaped to become the year where low latency inference can really start emerging and take off in the following years to come. So thanks to Saba and the team, we've been able to get early view of the TPU 8i architecture to try to understand what are the changes between V7X and 8i and how it relates to low latency inference and how it can enable these new workloads that we're pioneering. So what we're seeing is that, in a nutshell, because we can dig in very, very deep into this, but in a nutshell what we're seeing is that we're able to run 6 times larger models on what we predict will be an 8i compared to v7x, while maintaining the same latency threshold. This allows us to deliver better quality models, better customer experience at the same thresholds of latency and cost. And in AI, we're also targeting to reach drastically larger memory so that these models can remember more in time as they're doing their thinking, and also hit even hundreds of frames per second of inference, delivering completely unprecedented results. So let's take a look at 5 case studies of how we accomplish this, and this is going to get rather technical. So the first one, how can we put on 8i models that are 6 times as large as the ones you can put on v7x without hurting latency? It comes from 2 places. The first is what Saba mentioned, was the 3 times larger SRAM memory on chip. That gives us the first 3x because we can have 3 times more activations on the chip, stored on the chip itself as we're running the model. The second place is the ICI network. By having BoardFly, we're able to actually shard on twice as many TPUs without hurting latency. So we get the 3x from the larger SRAM on the chip, 2x more chips that can run a single model, and this gives us a total of 6 times larger close SRAM memory that's close to the computation units, and so we can actually use for low latency inference. The second challenge that we have, and this is actually a very, very hard challenge. Think about it. We aim to generate hundreds of frames per second. That's a frame every few milliseconds. To do that, we have to make sure that the entire chip is working synchronously without any barriers and any asynchronous stops. There are lots of different components in the chip, and we have to make sure they all work in lockstep with very, very critical short latencies, and we can't wait for them to synchronize with each other. TPU overcome this with a fundamental architecture that is very good for synchronous behavior. The chip itself, if you look inside a single core and you look at the VLIW assembly, it is all built to be synchronous and to make sure all the components inside a core all work at the same time with the same clock. The second part that is very interesting about TPU in the sense of synchronization is that in every chiplet we only have 1 core. And so this reduces the need to synchronize inside a chiplet. There's only 1 core, not multiple cores, and so you don't need to break and wait when you're synchronizing across the chiplet. So together, this really gives us the ability to avoid synchronization bottlenecks and make sure that we can deliver frames every few milliseconds. The third part actually relates to the model itself even more. World models have inherent sparsity. We have a lot of sparsity when we're generating the world because, for example, if I'm generating this room right now, most of the frames aren't changing. The seats here in this room, they're not changing. Maybe you're moving around a bit, I'm moving around a bit, but the screen behind me didn't change that much. And so we have this very dynamic sparsity that changes based on the world that we're generating. If it's a fast-moving world, we have little sparsity. If it's a slow-moving world, we have a lot of sparsity. But we can't predict the sparsity ahead of time. We have to observe it dynamically as the models are even being run. Now, to enable that, we need to build an entire toolkit of sparsity-aware kernels and make sure that in real time they compute what sparsity they have to use. We can do this because of 2 core reasons. One is that the TCS, the Tensor Core Sequencer, can make dynamic control flow decisions as it's being run, so it doesn't need to be programmed ahead of time of where the sparsity will be. And 2 is that the sparse core enables us to have fine-grained dynamic operations. Together, this gives us a very, very wide variety of sparsity mechanisms that we have that we can change as we're running the model based on actually what the inference demand needs. Moving on from the hardware and the model layer, we go into actually the developer tooling. We're building kernels that run in the microsecond latency speeds. If we have a kernel that takes just a few microseconds to run, how are you going to debug it? How do you build these kernels? And to enable that, we really need profiling tools, for example, XProf, that can sample at the nanosecond latencies so that when we're building these kernels, we can actually understand what's happening inside of them at latencies that actually allow us to see where we have bugs and actually program such low latency kernels very efficiently. To wrap this up, let's look at the 5th and last case study. A recent trend that emerged in low latency workloads is megakernels. It's building 1 kernel that runs the entire model all at once. Now, developing megakernels is notoriously not fun. Trust me, been there, done that, you do not want to do it. But Palace provides a very efficient interface to just slightly alleviate this pain. One of these interfaces, for example, is that we can use Palace to manually interject both memory and collective operations and run them at the same time in one single kernel. All in all, when looking at 8i and seeing what we believe it can do compared to v7x, we're seeing superior low latency performance for these new cutting edge use cases that we're going after. At Descartes, we focus on building the best infrastructure for leveraging the most cutting edge AI accelerators. And this lets us deliver the most state-of-the-art agentic performance today and unlock the new category of world model products. This lets us create a completely new experience for customers and end users. We're very excited to see what you build with our models and what we get to build with the new AI platforms that are coming up right now. Thank you all very much. Saba, back to you.
Thank you so much, Din. Thank you so much for giving us a sneak peek into world models, their use cases, and how TPU 8i is going to drive innovation for these frontier models. Now, before we conclude, let's quickly do a recap of some of the key takeaways. Number one, Google just unveiled our 8th generation TPUs, TPU 8T optimized for training, and TPU 8i optimized for low latency inference and RL sampling, with the new native PyTorch frameworks experience. Number two, the new 8th generation TPUs use new and specialized architecture to deliver up to 2.7x performance per dollar for frontier AI models. And last but not least, this is why leading AI labs like Descartes AI and enterprises all over the world are leveraging TPUs' capabilities and optimizations to build the world's most advanced frontier models, like world models. Now let's take a quick look at how you can get started on your TPU journey. Please check out several other TPU-focused breakout sessions throughout Google Next, BRK 2175 on Cloud TPU Experience, BRK 1069 on Serving on TPUs. Also, take a moment to check out the TPU 8T and TPU 8i chips that are on the showcase floor. This is a once-in-a-lifetime opportunity to interact with these chips up front. Visit the TPU website to get started on your TPU journey.